Make sure that you read these sections in your textbook before you continue with the rest of the lecture. You need that background information. So we need to understand a few things about heterogeneously catalyzed systems. Those are systems where the catalyst is a solid and our reactants and products are in a liquid and or gas phase. We require contact between the reactants and the catalyst for the reaction to proceed at a decent rate, and some transport phenomena are involved in this process. Most solid catalysts are highly porous. We can imagine that they look rather like sponges with lots of internal surface area. These pores create a huge amount of internal surface area, in excess, in fact, of hundreds of square meters per gram. The solid and this matrix of pores actually creates support for the catalytically active groups or atoms, so the active sites in our catalyst. For instance, in many cracking reactions, the reaction is catalyzed by an acid-like functional group that is supported by a metal oxide structure. When these catalysts are placed in a reactor, the flow conditions may result in the formation of a stationary boundary layer. So this is due to viscous effects, momentum transfer, and this no slip condition at the wall. This is drawn as a perfect little sphere, but it's actually more in the shape of a little droplet. But the implication is that there's a viscous boundary layer surrounding this catalyst where there is no bulk fluid motion, and the reactant can only reach the catalyst through diffusion. So when we have a reaction that needs to be catalyzed by our active groups, and our favorite reaction where A goes to B, component A is now happily flowing in the bulk of the fluid, but in order to be converted to B, it must travel quite a bit before it can react. First, it needs to diffuse through this boundary layer. So during this external diffusion process, no reaction takes place because there are no catalytically active groups in this boundary layer. Then it must diffuse through the pores into this matrix so that it can effectively utilize all the active sites that's available, not only the ones at the surface layer of our catalyst, but even the ones inside our catalyst particles. And during this process, diffusion and reaction takes place simultaneously. There are some aspects about the geometry of solid catalysts that you must know and really know well, so that it doesn't become a hurdle to you when you deal with the concepts that we will discuss after the break. Please do not underestimate the fact that you need to be really comfortable with these conversion factors. In the end, we want to be able to express our rates, all our rates, per kilogram catalyst in our reactor or per volume of our reactor. So in this course, we are only going to consider spherical catalyst particles. Please note that there are many shapes for industrial catalyst particles. So these definitions and equations that are shown here, you actually, you can Google them, but my advice is that you memorize them. You can forget about them after the 6 months of this course. So the area of a sphere we can express in terms of the particle diameter. We can express the volume of a sphere in terms of the particle diameter. The density of the catalyst particles, not to be confused with fluid density or the density of the packed bed, in kilograms per cubic meter catalyst particle volume. And then in a packed bed reactor, the amount of catalyst in the bed, so it's the kilograms of catalyst in the bed per volume reactor, can be calculated by considering the amount of catalyst per cubic meter catalyst particles and the bed porosity. In a CSTR, the mass of catalyst per volume reactor is calculated by the catalyst concentration in the bed, kilograms catalyst per cubic meter reactor. So important to note that this SI, the total porous matrix area in square meters per kilogram catalyst is not something that you can calculate using the catalyst geometry. It must be measured with a specialized instrument like a BET, cannot be calculated. But we are for now interested in external diffusion, so the external catalyst area, surface area per kilogram catalyst. That is what we are interested in, because that is the area to which our reactants must diffuse over that boundary layer. That is the first process where we are going to start. So we denote that parameter as AM, that's the symbol we are going to use for the area, external surface area of the catalyst particles per kilogram catalyst. Make sure that you agree with the equation that I derived here. For a packed bed reactor, since we can write the catalyst density in terms of the bed density, we can also calculate this parameter in terms of the bed properties, the bed density and the bed porosity. That's not true for a CSTR because those concepts are not relevant for a CSTR. And the last one that we need to be able to calculate or derive is the area, external catalyst area per volume of my reactor. So an easy equation to remember is that is the external area per kilogram catalyst multiplied by the amount of catalyst per volume reactor. For a PBR, that parameter is the bed density. So if we look at that equation, that is why we just have the bed porosity to consider to calculate that AC, which is the external surface area per volume reactor. And in a CSTR, the amount of catalyst per cubic meter reactor is equal, denoted by CCAT, the catalyst concentration. So if I just multiply this equation, AM by CCAT, this is the resultant expression. Please take some time to get a very good handle on these two conversion factors before we start with the discussion on external diffusion effects.